add two vectors. If you go to Program, I'm going to show you a program that I've already created that you can copy down, and then we'll try it out. This one's called Vectors. It's not user-friendly, but you should understand what it's doing. Here's what it looks like. What I have here is two vectors. I prompt for the magnitude of vector r and its angle, and I'm using r and theta for those keys. And for the commands, I'm using in my remember your angle key here. If you press second angle, you'll find this command. It's polar coordinates to find the x component of the vector and the y component. And you have to enter these variables and use the comma key. The comma key is right here, right above the 7 key. And you have to enter your prompts for the second vector. I called my second vector vector S, and I called its angle just O. And you do the same thing, find the x and y components of S. And the complicated part is down here. Scroll down here. Finding the magnitude of the vector. There's quite a bit to enter in here, but there's another command in your angle commands. If you go to your angle command, you'll find this way of calculating the resultant of the vector using these polar coordinates, where you have the magnitude and direction, or the radius and the angle. This right here will give you the magnitude of the vector. Notice I had to put a parenthesis here to start it, and then enter a second parenthesis. And I'm putting the same command you see up here for the x coordinate, or the x component, and also the x component of the second vector. So I have the x component of the first vector r and the second vector s. I'm adding corresponding components, and then there's a comma, and then I add the corresponding y components of both vectors. If you set it up just like this, this will calculate the magnitude of the vector. It will actually add those corresponding components, and then it will apply Pythagorean's theorem to give you the actual magnitude of the vector, the resultant vector, once you add these two. And then to find the direction, you do something very similar. Now I put a pause command in here, and you can find the pause command when you press Program. You'll see it in the very first column. It's just to give you a moment to look at what has been calculated before it does the final step. And the final step looks just like this long drawn out step to find the magnitude, except we're using a different command here in the front. It has the theta angle in it. You find this in the angles command too, where you plug this in to find the angle, the direction of this vector. And you plug in everything just like you did for the magnitude, where you add corresponding components. And what this does, it takes the inverse tangent of the net y component and it divides by the net x component. So you should take a moment to copy these commands down into your calculator and see if they work. We'll test them out. So you want to prompt r and theta, then do the display, the polar coordinates for your x and y components, enter just like this. Then do the second vector, call it S and O. I call this my ROSO program. I have a much more complicated version of this that's more user-friendly, but this is all you need to just get started with this. And also find the components of those vectors. And once we find, remember, we decompose each vector into its x and y components. Once we find the components, then we're ready to find the magnitude and direction of this resultant vector. So this first command here will give you the resultant, and the second will give you the direction. Alright, so let's run this program. Let's go back to, let me quit out of this. Go back to Program, and I want to execute it. So there it is. I want to press Enter. You have to press Enter again, and it'll ask me for a vector. Now I have a few I've already worked out. Let's do this one. Let's say we have a vector that's 70 meters. Now Enter. And it's at 50 degrees with the positive x-axis. What are the x and y components? Well, you could solve for the x component by taking 70 and multiplying by the cosine of 50 degrees. And you could find the y component by taking 70 and multiplying by the sine of 50 degrees. But this will do that for you. When you press Enter, it'll give you your x component first, so that's about 45 meters, and your y component second, that's about 54 meters. Or not your, yes, that's component, 54 meters. So x and y components in order. And now it would ask you for the second vector before it adds these vectors, because we need to know the components first. So for the second vector we have 50 meters. For the direction, let's make it minus, use your change in sign key, minus 20 degrees. Alright, and let's press enter. Now this is not only going to give us the x and y components of this vector, it's going to add these two vectors. So the third answer here will be the resultant. And then it'll pause, and then I can press it again to get the direction. Alright, so the x component is 47 meters. The y component is negative 17.1 meters, so that means it's in the negative y direction. And then the resultant of the vector is 99 meters. 99 meters. And what's the direction? And this direction will tell us what quadrant it's in. So I'm going to press enter again. So the direction is about 22 degrees. So there you go. That's one way to do this. Now if you wanted to verify all of this, you could do the first vector, or let's just do the second vector. 50 times, if we want the x component, we do the cosine, in this case, of minus 20 degrees. And let's see. Yep, 46.98, so and so on. And if we want y component, do 50 times the sine of minus 20 degrees using these acute angles. And there you go. So it works. Now we can run this program again. Let's run this program again. I'll just try some different numbers. Let's see. I had a few examples here. I misplaced them. Let me find the one I had here. Let's try this one. Let's try, how about 100? Think about that. 100. Let's make that 100 meters per second. Let's talk about a plane flying, say, due north. So its magnitude would be 100 meters per second. It's flying due north. So what would the angle be? If you're flying due north, what would you make the angle? Well, if you use our standard coordinate system, we'd be flying at 90 degrees. So we'll make that 90 degrees. Alright, so what would the components be? Can you guess? Would it have an x component? No, just a y component. You should guess that. So the x component should be 0, and the y component should be 100 meters per second. Alright, let's say there's a wind. There's a wind that's due east. And let's say its speed is 100 meters per second, and it's due east. So what should be the angle of this wind if it's due east? Well, if it's due east, shouldn't it be 0 degrees? Well, let's put 0 in. So what are the components? Did you guess 100 for the x component and 0 for the y? Well, you'd be right. And then for the resultant vector, because this actually would form a square, it would be the diagonal of the square. Remember that would be 100 times the square root of 2 times 1.41 and so on. So it looks like it works out. The resultant would be 141 meters per second. What would the direction be? Well, if it's a square, it should be 45, right? So press enter again. And look, you got 45 degrees. So this would be an example of adding two vectors. And let's see if I have another example for you. That was a pretty good one. Sorry, I misplaced my examples here. Let's see if I have another good one. So you're learning a little bit about basic programming, which stands for Beginner's All-Purpose Symbolic Instruction Code. And you can write your own programs and create your own problems. Let's do one more. Let's run this program again. And just press enter. I'm going to say we have a vector that's 141, and I'm going to give you a unit of force in, let's backtrack that. 141, instead of pounds, we're going to use what are called newtons. It takes about 4.45 newtons to equal 1 pound. So a newton is about 1/4 of a pound. And let's say we have a force of 141 newtons. It's at an angle of 30 degrees. Then we're going to have another force on the same object. By the way, there's the components. We have another force on the same object at 131 newtons, but it's pulling, or you could say pushing, at an angle of negative 100 degrees. So let's put in the minus 100. This will give the components and the resultant. So what would be the net force on this object? There's two forces, 141 and 131. But what's the net force on this object? Well, let's see. The net force would be 115 newtons. 115 newtons, and this would be the x and y components of the second force. And what would be the direction of this force? I mean, there's one pole, or you could think of it as push, which depends on how we set it up, at 30 degrees, and the other one's at negative 100 degrees of different amounts. What would be the direction of the net force, which would produce the net acceleration? Well, if we press enter, it predicts that it would be at negative 30 degrees. And we might use this type of application when we're talking about force tables, where we have a disc in the center of a circular table that has strings attached to it. Strings go over pulleys where you put weights, and you pull on this ring from all different directions, and you can predict the forces on the net force on the ring and the direction that it will accelerate. We'll talk about that later, but please enter this program into your calculator and test it and see if it works for you. There's more to this program, but this is a small sample. Thank you.